speech processing, assistive technology, hearing aid, signal processing, and acoustic engineering. He also leads 2 centers of excellence at AIISH, the Center for Rehabilitation Engineering, Acoustics and Biomedical Engineering, and the Center for Augmented and Alternative Communication and Sign Language. His research includes developing automated tools for diagnosing speech disorders, robotic models of speech production, advanced AAC systems, and improving acoustics, communication, focused spaces. Dr. Abraham holds a Ph.D. in electronics and completed postdoctoral research at the University of California. He has guided several major national research projects funded by DSD, DBE, and AIISH, and has published more than 45 books, including journal articles, book chapters, and conference papers. We are truly honored to have you with us today, sir. On behalf of organizing committee, I wholeheartedly welcome you, sir. Now I request you to take over the session.
Inside of hearing is what is there inside the hearing aid, and how the hearing aid processes the signal, and what are the complexities involved in that, and how AI can be incorporated into hearing aid signal processing, and we will towards the end we will see which are the gaps which can be addressed as research problems. Now, hope all of you have seen a hearing aid at least once. All of you have seen, at least you must have seen a person with a hearing aid. Right? So, you have heard in the last 3 days about the hearing mechanism. So when we think about the hearing mechanism, there are so many add-ons comes along with the process of hearing. The hearing is not just to hear the sound. Along with that, there are certain add-ons which are coming. The first one is the speaker identification. Many times nowadays you have the caller ID displayed on the mobile, but when you attend calls through a landphone, many times the person on the other side, without revealing his identity, you will be able to identify him from his voice. So that is called speaker identification, right? The ear does that automatically, okay, based on some parameters of the voice of the speaker which is already fed in the brain. So along with the process of hearing, that comes. The second one is listening to desired sound amidst noise. Okay, so now the class is very quiet. If there is another classroom nearby where the teacher is absent, students will start chatting in loud sound. But even at that time also, you will be able to hear the speech or the talk of the person whom you want to talk. So here it has a beautiful feature to suppress the noise and tune to the desired sound. The third one is sound localization. So I'm standing here, if somebody calls me from the back, what will I do immediately? I'll turn. So this information that he is calling from back is given by my ear along with the process of hearing. It's called localization. Next is pitch perception. Those who are familiar with music, you know about the pitch and importance of pitch in music. Even in speech, pitch is very important because it is the pitch which decides which conveys the emotions along with the sound, which we call it as prosody. Prosody, speech prosody is basically based on pitch. So the ear can clearly distinguish from the speech the emotion of the person. Okay, emotion that affection is a big topic of research nowadays. So the speech carries the emotion. Okay. So if if I'm going to speak angrily, you can easily recognize from my speech that I'm angry. Okay? Especially when we talk over the phone. If the other person is angry, how do we recognize that he is angry? From his speech only, from the tone of his speech only. So that is another advantage which the ear is along with the process of hearing. Next is the music perception. See, when we listen to music, recorded music, we clearly can distinguish which are the music instruments included in that music. Okay, whether veena is there, violin is there, guitar is there, keyboard is there, the percussion instruments, tabla, mridangam, all of them are there. We can easily distinguish with the help of the ear. And the last one is speech perception. When I am talking to you, you are hearing me, and along with that process, you are also comprehending what I am telling you. Okay? But if I speak in my mother tongue, you will be able to hear me, but you will not be able to comprehend what I am speaking. You will not be able to understand what I am speaking. Okay? So this is a beautiful mechanism of the ear where it perceives the lexical content of a message which is being spoken, and you will be able to understand that. Now, the last line is very important. Okay, so this is achieved when the sounds are processed by the human ear and the brain. So all these features are a net result of the combined processing of the human ear and the brain. And when the ear is affected, when you have hearing problems, all these features are going to be affected. Okay, not only the process of hearing. So that is why we require signal processing in hearing aids. People think that hearing aids are just amplifiers which make sound louder. Not at all. They are not amplifiers. They are processors which are going to support all these processes which the ear will be doing in the normal process of hearing. So that is how the hearing aid signal processing is complex, and that is why you have an FDP program exclusively on the hearing aid signal processing. Now, when the hearing impairment happens, when the hearing mechanism has a problem, the first thing what happens is increase in the bandwidth of cochlear filters. Yesterday you had a session on cochlear signal processing, and you have seen that there are 1024 bandpass filters in the cochlea, which is responsible for our hearing of different frequencies from 20 Hz to 20 kHz. So what happens with the impaired ear is that the bandwidth of the filters increase. Okay, so then you know that when the bandwidth of the filters increase, what happens? There will be overlap between the bands, and you will not be able to hear certain frequencies. There will be cross interference between the adjacent frequencies. All this spoil your hearing mechanism. So that is the first thing which happens along with the hearing impairment, which we have to correct with the help of hearing. Then the next one is reduced ability to separate out desired sounds from competing noise. So once you have hearing impairment, you will lose that ability to listen or tune to a sound in presence of noise. Why that happens, I have a video to show that I will show you later. The third one is called the fine structure cues. Now, for each of the words to be intelligible, the words which I am speaking, if it has to be intelligible, that intelligibility depends on certain cues. You must have seen that when you talk to little aged people, many times they will ask you to repeat the words which you are speaking. Okay? Can you please repeat again? So that is because of the hearing impairment, they are missing some cues which are carried in each of the words. So they are known as fine structure cues, which makes the similarly sounding words distinguishable or comprehensible. Then the inability to different components of speech. So speech has got different components. Like basically, if you classify the speech into two broad categories, it has got vowels and consonants. And any word you take is a combination of vowel and consonants. Okay. Now, if I have to hear a word clearly, say for example the word cashew, I have to clearly hear the vowel and the consonant. Which are the vowels? Sounds A, E, O, U. They are all vowels. vowels, and all other sounds, say ka, ba, cha, da, we call them as consonants. So it's a mixture of vowels and consonants. For the speech to be clearly intelligible, the vowels and the consonants should be separately audible and intelligible. So you will lose that ability when you have problems in your hearing mechanism. So hearing aid has to correct that. Reduction in hearing sensitivity. Okay, so you will have reduced sensitivity. That means the sound has to be louder. Okay, if it is a low intensity sound, you will not be able to louder. So all these are effects of hearing impairment. So what we expect from a hearing aid, or what we expect from hearing aid signal processing, is solution to all these problems. Okay, so the hearing aid should do the enhancement of the signal. It should do the noise reduction so that you can hear speech in noise very well. Then it should give a cleaner sound. It should have a better shaping of the frequency response, because your cochlear filters are broadened. So that broadening in the cochlear filters you have to compensate by better frequency response. And then you need the localization. So for that you need directional microphones to localize sounds from this sound, that is which direction it is coming. So the hearing aids are the most fundamental technology in correcting hearing problems. So we call it as a rehabilitation of person with hearing impairment. So that means correcting hearing problem. Hearing aid is a fundamental technology, and the primary function of the hearing aid is not to amplify, not only to amplify, to process the acoustics filter such that the signal which is reaching in the inner hair cells. I'm sure you must have heard about inner hair cell and outer hair cell in yesterday's talk, the role these play in the process of hearing. So the hearing aids have to ensure that the signal reaching the inner hair cells is close to the signal that would be presented to the inner hair cells by a healthy auditory system. So whatever a healthy auditory system does, or whatever processes it does, that those processes the hearing aid has to do, so that as you and me listen to the sound, the hearing aid user should be able to listen to that. And for that, it should address the frequency dependent hearing loss and compensate for the deficiency in the dynamics caused by the hair cell damage. So those who are not very familiar with the hearing aids, these are the different types of hearing aids. And this classification or this naming is based on the way in which the hearing aid is worn. Okay, so first we have the body worn hearing aids, which is worn on the body or in the pocket. Then we have behind the ear hearing aids, which is worn behind the ear, as we can see in the picture. Then we have receiver in the canal hearing aid. So you can see that the earphone is out of the hearing aid. The difference between the second and the third one is that in the second one, the earphone is inside the hearing aid, whereas in the third one, it is outside the hearing aid. Then we have the small versions. The first one is called completely in the canal. It is also known as invisible in the canal. You will not be able to see the hearing aid at all. So if you see the picture there, bottom picture, you are not seeing any hearing aid. It is completely inserted in the canal. Then we have in the canal. So the surface of the hearing aid will be visible. And then we have in the ear. So these are different types of hearing aid based on the way in which the hearing aid is worn by the user. So now coming to signal processing, the first digital hearing aid which was built with the help of a digital signal processor was launched in 1996, and after that now it is very difficult to find a hearing aid without a DSP. Okay, so all hearing aids have got DSPs, and this is the basic architecture of a hearing aid. Okay. So it has got a microphone which is going to hear for you, which is going to receive the sound. Then after the A to D conversion, then you have a DSP where all the signal processing that you are going to see in today's presentation is done. And after that it is converted back to digital, and then it is given to the earphone. So earphone in hearing aid terms we are going to call as a receiver. Okay, so in all the future discussions the word receiver represents the earphone. The speaker of the hearing aid we are going to call as LC. So, having seen a broad overview about the hearing aid, now we will see the signal processing challenges in the hearing aid. And then we will see how these challenges are solved in the signal processing which is done in the hearing aid. The first challenge which the signal processing has to address is speech and noise, isolating and enhancing a target speaker from background noise. Now all of you are from the electronics background, so you will be thinking, what is so great about removing noise? Easily with a filter. Now we have so many filters available, right? With different technologies, filters are available. So easily you can filter out the noise. But here the task becomes difficult is because what you want to hear as speech and what you perceive as noise, both of them have the same spectral characteristics. The frequency is same, okay? The speech is also, even suppose I want to talk to you and all others are talking. The frequencies at which, or the spectrum at which all of you are talking and the spectrum at which I am going to talk to him is same. So it's very difficult to isolate the noise with a filter. So that's why in hearing aid, noise elimination never happens. If noise elimination has to happen, you have to eliminate speech also. Okay? So that's why it is called noise reduction or noise control. So that is one major challenge which we have to address in signal processing. How do we address that? We will see in the slides to come. The second problem which we face in hearing aid design or in signal processing is the complexity in the real world. Now, when you wear a hearing aid, you have to face different listening situations in a day. For example, today you started from your home. So your home is a different listening situation where there is not much noise. Okay? Then, suppose you are taking a vehicle and driving the vehicle. So that time, all the traffic noise. So the hearing aid has to work in the traffic noise. That's a different listening situation. Okay, then you come to the college. That's a different listening situation. In between, you go to a market to purchase something. That's a different listening situation. Okay, so the hearing aid has to face all these situations and need to have different signal processing mechanisms to process some of these different listening situations. So most of the time, what happens is when the design is done, these conditions are simulated in the lab. Okay, and solutions are because you cannot take it there and do the design. You cannot record it and do the design also because how many situations you record. Each situation is different. For example, if I design for a bus stand at Mysuru and a bus stand at a village, it's totally different, right? So when I go to a bus stand at Mysuru, it has to have a different program, altogether different strategy for processing. So these are the complexities in the real world situation. And when I say market, if I go to the main market here, the situation is different. But if I go to a supermarket, the situation is different. If I go to a mall for shopping, the situation is different. So all these complexities, it has to address. The third challenge which it has to address is called the occlusion effect. So most of the time, what happens is when we wear the hearing aid and when you speak, okay, that will sound too much loud to you. That effect is called occlusion effect. So we need to identify the person's own voice, and when the person is speaking, we need to have a different signal processing strategy. And when the hearing aid is receiving speech from others, we need to have a different signal processing strategy. The next problem which the hearing aid faces is called acoustic feedback. So you must have listened several times when we use public address systems like this. If I take the mic and go near the speaker, what will happen? It will start howling, sound will come. Now, in the case of hearing aid, this microphone and the speaker are very close by. So the chances of this humming is more. And especially when you have to give a high gain hearing aid to correct for severe hip to perform hearing loss, the gain required is very high. So the chances of the feedback are more. So you need to address that also, because the moment the feedback happens, it no more functions as a processor, it functions as an oscillator, which will give you only whistling sound. The last problem and the most severe problem which we have to address is the delay in processing or the processing time. Okay? So many a times we, when we go for programs like this, the first question that people will ask or the participants will ask is, sir, we have a mobile with so much of processing capabilities. Why can't we use this mobile as a daily? Why do you need an extra device? Because the processor in the mobile is far, far better in terms of all its features compared to the processor in the hearing aid. So why can't we use this mobile as a hearing aid? The answer is this. Because the processing time here is very important. So you cannot take a processing time more than 8 milliseconds. Because when you are listening to speech, you listen to speech through two mechanisms. Two mechanisms are aiding you to listen. One is through the ear, and second is through the lip reading. Right? If I speak to you, turning this side, I'll challenge you that half of the words you will not be able to comprehend clearly. Okay? So this lip reading, so you are listening to me, you are facing me, and my lip movements are aiding your hearing. Okay? So that we will lose if the processing time is more than 8 milliseconds. Some of the videos when you see, you must have observed that the audio doesn't follow or doesn't sync with the lip movement. So that then it becomes so irritating to you, right? You will stop, if it is a movie, you will stop watching that movie, because this is very important in your hearing concept. So these are the 5 major challenges which we have to address when we consider the hearing aid technology. So with these in mind, now let us move on to the different signal processing task which we are going to take up in. So before that, when you have a hearing problem, to assess your hearing problem, there are different tests. And one of the most common tests or fundamental tests is called audiometry. In audiometry, what is being done is you will be asked to sit in the inside room. It's a 2-room situation. So from this side, this is the audiologist who is testing your hearing level. So she uses an instrument called audiometer, and this is done in a soundproof room testing. So she will be presenting different tones. It will be pure tones, okay, of different frequencies, and these frequencies are from 250 Hz to 800 Hz, at 8000 Hz, at distinct frequencies. So she will start at 250 Hz, then the next frequency is 500 Hz, next 750, 1000, 1500, 2000, 3000. So at these frequencies, she will be presenting the tone, and she will be presenting it at a particular intensity. Okay? And she will be asking you, when you hear that tone, please raise your hand. Okay? So first she will present at the level you are not hearing, then she will increase the level. So till you raise the hand, this will be continued. Okay? So these levels at which you are hearing, that will be marked on the sheet, which is called the audiogram. So this is a plot of frequency versus intensity. On the horizontal axis you have the frequency, vertical axis you have the intensity. At each intensity, what you are hearing at different frequencies. You can see the frequency markings on the top. The first one is 250 Hz, next 500, 750, 1K, like that. Okay, at what intensity you are hearing. So if you see here, you can see that this particular person, for his right ear, he is hearing 250 Hz at 80 dB. So that means he needs a sound louder, more than 80 dB, the level at which you are hearing. So if you are hearing it at 0 dB, he is able to hear only at 80 dB. So that means intensity increases with that. So after plotting these audiograms, we can see that the response is frequency wise. Okay, so at each frequency, he is hearing at a different level. So now when we compensate this with the hearing aid, we have to give a gain proportional to this at each of the frequencies. So that gain calculation we call as target gain curve. What is the gain to be given at each frequency? That is calculated based on this audiogram. Okay, so this is the target which we have to achieve with the hearing aids. And most of the hearing aids have got programmable capability. It can be programmed. The gains can be programmed for each frequency. Okay, so that is one part in the hearing aid fitting. The hearing aids are programmed as per the audiogram of the customer. So from person to person this will vary because your hearing levels will vary person to person. So based on each one's hearing level, the target gain has to be achieved. Now once we finalize this target gain curve, the hearing aid has to implement that. It means what? This particular hearing aid, it has to give 30 dB gain at 250 Hz. It has to give 38 dB gain at 500 Hz. It has to give 50 dB gain at 1000 Hz. But different frequencies you have to implement differently. Now, to do this, the first thing which it has to do is it has to divide the incoming sound into different frequencies. Okay, so the incoming sound is from 20 Hz to 20 kHz, which is our audible frequency. That has to be divided into different frequencies. So one way of doing this, so this process of dividing the incoming sound into different frequencies is called channel separation. And one way of doing it is the use of filter bands. So if you want to divide it into say 10 frequency groups, you have 10 band pass filters, each with its own transfer function, different transfer function because the gain to be implemented at each frequencies is different. So you now when we implement this with the filter band, in fact 5 years before all the hearing aids were using this. But what we are doing when we implement like this is you are splitting the sound, cutting the sound which you are hearing into pieces, then apply the gain for each frequency band. After applying the gain, you are then recombining the signal. Okay, so in this process, you are going to lose the naturality of the speech signal because the sound, the sound which is processed or the speech which is processed through the hearing aid will be totally different from the speech which you directly listen. Okay, so that's why this picture is there. When you have a toned note, suppose you have a 500 rupees note, it gets toned. What will you do? You apply a gum neatly. You make all efforts so that the person to whom you are handing over the note should be able to see. Probably you will give it to a shopkeeper. The same speech will return the note back because he knows that it is a toned note. Okay? The same thing happens with the signals processed through the ear. You are cutting it into different frequencies, applying different gains, and then recombining. Okay? So that sound which comes out through that hearing aid will be very different from what you hear in your natural way. So if that continues, what will happen if you give this hearing aid to an old person or your father or your mother or your grandfather or grandmother, she will use it for 1 or 2 days. After that she will silently remove it and keep it there because she feels that without this it is better for me because the sound which is coming through this is totally different from what I hear. So it spoils the signal, it splits the signal into a different number of frequency bands which spoils the naturalness of the signal. So that's why an advanced type of giving the different gains at different frequencies, an advanced filter called controllable filter approach has come. So the hearing aids which have this controllable filter in place, they are known as channel-free hearing aids, that is known as channel-free signal processing. So now in this channel-free hearing aids, what is being done is the splitting into different frequencies is not done. So what do you see here are two parts of the signal. One is the audio part, those dark arrows represents the audio part. And the second one is the non-audio part. So audio part goes directly through the filter and then it goes to the earphone or the receiver directly. And in that part you have a FIR filter. So these filter coefficients are controlled by the bottom section. So the division into different frequencies happen in the bottom section, which is not going to affect your main signal at all. So in the bottom section you divide it into frequencies and then based on that you decide the filter coefficients. And these coefficients are fed to the IAR filter. So IAR filter does not get involved in splitting it into different frequency components, but it takes the coefficients based on the amplitude levels at different frequency components. So this has solved that naturalness issue to a great extent. Okay, so why we do warping there, it's warped FIR filter, why do we do warping there, is to match the filter's response with the response of the cochlea. So if I show you the response of the cochlear filters, it is like this. So you can see that the bands are crowded at the low frequency region, whereas you have fairly less number of bands at the high frequency region. So the cochlea functions in a warped way. Okay? So it's not linear. The response of the cochlea is not linear. To incorporate that into the FIR filter, we are using warped FIR filter there. So this controllable filter gives it, do not divide the signal into narrow frequency bands. It does not alter any features of the speech. It preserves all the contrast cues in the speech, and it closely resembles the cochlear non-linearity. So this has solved to a greater extent the naturalness, preserving the naturalness in the speech segment. Okay? So that's why the sounds which are coming out through the present hearing aid, even though they are very not very close to the natural speech, that the difference has reduced here. So that was task 1, to divide the speech into different frequencies and to give frequency dependent gain. The second task here, this is very important task. This is to reduce the range of input levels. So now, when we listen to sounds, we will listen to very soft sounds also, very feeble sounds. If somebody is murmuring, we will listen to that. And if somebody is shouting also, we will listen to that. And if there is some loud music system, we are supposed to listen to that. So the range of levels to which the human ear responds in the day-to-day life is very wide. Okay? You can listen to somewhere near 0 dB sound also, and it is your ear is exposed to up to 140 dB sounds in your daily life, in your routine life. Okay? Some announcement system comes with loud sound, the ear is supposed to listen to that. And while going on the road, somebody's birthday is there, cracker is being roasted, you are supposed to listen to that. So this wide range of sounds which the ear faces in its day-to-day life is from 0 dB to 140 dB. Remember, dB is a logarithmic scale, so 140 dB is almost 2 lakh times compared to 1 dB of sound. Okay, so that much is the range of levels to which the human ear responds. Now, for an impaired person, because he has problems in the ear, the range of his ear, this range we are going to call as dynamic range, and the range of sounds, the range of level of sounds to which his ear responds, that also gets reduced. And that reduction is frequency wise. So you can see the graph there. At different frequency bands, the dynamic range is different. So if you see here, this is his dynamic range in this band from 250 to 500 Hz. This is his dynamic range in 100 to 1 kHz. This is his dynamic range. So this dynamic range means if he has to listen to his ear, the level of sound should be within this. Right? So if it is a loud sound, you have to reduce it. And if it is a soft sound, the low level sounds we are going to call a soft sound. If it is a soft sound, you have to increase that. Okay? So you have to fit the output of the hearing aid to the dynamic range of the listeners. That is the second task which we have to accomplish. So to accomplish this, first we should measure the level of sound which is coming there. Okay? First we have to see the intensity of sound, whether it is a soft sound, whether it is a loud sound. So if it is a soft sound, we have to enhance it. And if it is a loud sound, what we have to do? We have to reduce it so that it doesn't go out of the dynamic range of the user. So while taking your audiogram, while taking the audiometry, they will mark 2 things. One is the minimum level at which you can hear, and the maximum level at which you can withstand. Because if the level crosses that one, it causes a lot of difficulties for you. It causes headache, it causes pain and all. Okay? So the difference between this minimum and maximum level, we call it as dynamic range. So the second task which the hearing aid has to perform is compression of the dynamic range. That is what shown in the top picture. This is your dynamic range of sounds which you are facing. That has to be compressed to this level. And this compression is again frequency dependent. So different frequencies will have different compressions to achieve. Now to achieve this, you have to measure two things. One is you have to find out the frequency, and then you have to find out the level also. So this is done like this. You take the incoming signal, divide it into number of frequency bands. So as an example, I have shown how it is divided into frequency bands. After dividing it, you do the level measurement. What is the intensity of sound? And based on the intensity, then you have a compression characteristic. Compression characteristics means how much gain is to be given to each level of sound. If you see here, this is the level of the incoming sound. When the level is 40 dB, you are giving a gain of 10 dB. When the level is 50 dB, you are giving a gain of 10 dB. When the level is 60 dB, you are giving a gain of 9 dB. Like that. Okay? So for each level of the incoming sound, how much gain has to be given? That is given by the compression characteristics. Now, there are two compression characteristics here. This compression characteristics is for this one, this group of frequencies. This is for the next group of frequencies. Now you see a big difference here between the compression characteristics. For the same sound, whose intensity is 40 dB, we are giving 40 dB gain here in this frequency because his hearing sensitivity is very poor in high frequency. Right? So like this, if you have say 8 frequency group, you will have 8 different compression characteristics. So after deciding the gain based on this compression characteristic, you will assign that gain, and this is done to each of the frequency group. Finally, you will recombine. So this process is called wide dynamic range compression. So this is the second task which we have to achieve through the hearing aid. Now we move on to the third task. Whenever you talk to a person who is wearing hearing aid, and if you ask, what are your major concerns or the issues which you face with the hearing aid? The first answer, which some of them will give is that the device is physically uncomfortable because there is something which is there in your ear which keeps you irritated. Okay, so that is uncomfortable. When we start wearing specs, also in the initial days, at least first 1 or 2 years, what normally we do is whenever we want, we will put the specs. Otherwise, we just like remove it and keep it on the table or keep it in the pocket because this is an external device. This is uncomfortable to us. The same thing happens with the hearing aid user. The second thing which they are going to express is that it is not performing as expected. Okay, so too much of background noise is there, poor sound quality is there, so it is sounding totally different from natural sound. So this study, which was conducted in 2015, over about 1,000 users of hearing aids, they have come out with these findings that these are all the issues which are faced with the user. And the lowest satisfaction level was observed when the hearing aid users were trying to listen to a conversation in the presence of noise. Okay? So if you have to talk to somebody when you are standing in a restaurant, if you have to talk to somebody when you are in a what you call function, in a function hall, a marriage function or a housewarming function, or when you are in a religious place, in a temple, places of worship in a temple or a church. So you have to speak to people in presence of that noise, amidst that noise. And the hearing aid satisfaction level is only 50% in such situations. Now, I have a small video to show you what happens when the hearing, the persons with hearing problem, they are in presence of noise. Or
what most people don't realize is that having difficulty in background noise has a lot to do with the root cause of most hearing losses, which is the deterioration of outer hair cells inside of your cochlea, that's your hearing organ. These outer hair cells are responsible for taking the natural vibrations of sound as they enter your ear and amplifying them in order to trigger a neural response that travels up your auditory nerve to your brain. That's why we call these outer hair cells makes them susceptible to damage due to things like age, noise exposure, chemical exposure, and head trauma, to name a few. When healthy, these outer hair cells are terrific at taking soft level sounds from your environment and amplifying them enough so you can hear them. But even if some of these outer hair cells are missing, the human brain is usually good at taking what information it does receive and piecing it together so you can understand what someone is telling you if you're in a quiet environment. However, these outer hair cells are also responsible for helping you hear better in background noise. Now bear with me here because I have to give you a little bit more of an in-depth anatomy and physiology lesson. Approximately 5% of the nerves that innervate these outer hair cells are called afferent nerves, meaning that they take information from the ear and send it up to the brain. The other 95% of these nerves are efferent nerves, meaning they receive information from the brain. So why would an outer hair cell be innervated by so many efferent nerves and so few afferent nerves? This is because your brain actually tells your ears which sounds to send up the auditory nerve and which sounds to suppress. In a normal hearing ear, in a quiet environment, your brain tells your ears, yeah, go ahead and send all that speech information up. However, when you get into a background noise situation, the brain is sending signals down to the ear through these efferent nerve endings, telling your inner ear not to send up the noise information, but to send up the speech information. Now, when you have a hearing loss and you're in a quiet environment, your brain is still like, go ahead and just send up all the information, I'll piece it together, no problem. However, when you have a hearing loss due to the deterioration of these outer hair cells, your brain does not have the ability to send a signal down to your ears to tell it to suppress the noise from sending up to the brain. Of course, when you're in a noisy situation and you don't have enough outer hair cells, your brain is trying to send information down to your ear to tell it to suppress the background noise, but your ear never receives the signal and never can suppress the noise. That, my friend, is
So that is what happens when you have hearing problems. 95% of the hair cells which you have are to send information from the brain to the ear. Now, since those cells are damaged in your hearing mechanism, this communication is not happening. Okay? The brain is sending the message, but it is not reaching the ear. The brain is sending the message that you suppress the noise, but it's not reaching the ear. So what happens? The ear doesn't know which one to suppress, which one to enhance. So both signal and noise will go to the brain and you will not be able to hear the speech at all. So in this condition, the third main task which the hearing aid has to follow, that comes, which is called noise suppression. Okay? So here it is noise, not noise elimination. You cannot eliminate the noise, it's only noise suppression. Reduce the noise to a level that you can comfortably hear. Right? So suppose you are talking over a phone and the TV is loud. What you will immediately do, you will reduce the volume of the TV so that you will not switch off the TV. You will reduce the volume of the TV so that you can converse with the other person. So that means you are reducing your noise to a level such that you can hear the speech. Okay, so this ratio is called speech to noise ratio, SNR. So you bring the SNR to a level such that you can comfortably hear. So you are not bringing the noise to zero, you are lowering the noise level to a level that you can comfortably hear. And this cannot be achieved with one technique at all, because in the beginning I have told you that the difficulty here is what you want to hear and what you don't want to hear are in the same frequency range. Okay, so you cannot use direct filtering, remove this, take this. Okay, you have to do multiple procedures, multiple signal processing procedures to achieve this task. So most of the hearing aids use two common procedures. One is noise reduction at the microphone level itself. Okay, at the source level itself, how much reduction can be done, and after that at the signal processing level. So we will see how this is done at the source level. So what you see there is the microphone which is used in the hearing, which is a very small one. I have some pieces here which you can see. So just to get a feel of that. Small. This is outside. This is inside. This one. This hearing aid is completely inside the body. this limitation in that small hearing aid, you are compelled to use only a single microphone. So to achieve the noise reduction with the help of this microphone, we use a two-port microphone. So two-port microphone means sound can enter into the microphone through two ports. One through port 1, other one through port 2. So the port 1 will call as front port. So if I am using the hearing aid like this, the front port, the front through which sound enters, will be focused towards the front side, and the rear port will be back side. This is based on an assumption that whenever we are talking with someone, the sound which we want to listen comes from the front, and the sounds which we don't want to listen are in the background. Okay, so you see here, this is the front port. Sound enters through the front port, and then this is the rear port, which is from the back side, which enters through the back. The sound which enters through the front port will be the sound which we want to listen, plus the noise. Background noise will be there, and the sound which enters from the back side is only noise. What does diaphragm? We know that when microphone functions, sound falls on the diaphragm of the microphone. The diaphragm converts electrical displacement, and these displacements are converted to electrical signals. So when this microphone works, it responds to the difference in sound pressure between the two volumes. Okay, so that means signal plus noise is entering here, noise is entering here. The difference is signal plus noise minus noise. The noise cancels, it responds to only the signal. That is the concept which is followed here. So with the help of this dual, these are called two-port microphones, where you have two ports entering the microphone. So this is one technique with which the reduction is done, noise reduction is done. So that when we place the microphones, it will be like this. One port will be towards this side, one port towards this side. But the problem with this is you cannot change the directionality. Directionality is always towards the front, because front port is always in this direction. Now we have dual microphone system. In the other hearing aid which I showed you, the bigger one, so two microphones. So what these two-port microphone was doing, the dual microphone will, one microphone will be focused towards the front, the other one will be focused towards the rear side. And there, instead there you have something called as an electrical filter. So this filter characteristics you can change, and by changing these filter characteristics, you can change the directionality of the filter. In the earlier one, it was only possible to have one directionality. Okay? Whichever sound you want to listen, you turn that side and listen. But somebody is calling me from back, giving some important warning signal. That microphone will not be able to pick up that. But here, when sound comes from the back, it automatically changes the direction. So the rear mic becomes the front mic in that condition, and front mic becomes rear. This is called adaptive directionality, which is incorporated in the technique. So either by using a dual port microphone or by using dual microphone, you can cut down the noise to a great extent at the source end. So the specific directional pattern can be changed by changing the characteristics of the filter head. Now we will see how this can be reduced with the help of signal processing. But here the major challenge is the sound which you want to listen and the sound which you don't want to listen, both of them are spectrally the same. They have the same frequency. But still we will see what best we can do with this signal. Now this is the noisy signal. This is taken from the hearing aid only. So this, as it is written there, this is the speech signal for the word understand. So when I say understand in a noisy situation, what goes to the hearing aid is this. So in this you cannot see any signal there, right? It's full of noise. Fluctuations which you see there, it's all noise only. So now what can be done with the signal processing to reduce the noise a little bit? So what is being done is, first you take the input signal and split it into different frequency groups, okay? 3 or 6 or 10. It depends on the capability of the processor which you are using. So divide it into different frequency bands. As an example, we take 3 frequencies. After we divide it, after we split this, this is the output which we are getting. Okay, so in 0 to 500 hertz band, I'm getting that signal. 500 to 2 kilohertz, I'm getting that, and 2 kilohertz to 4 kilohertz. Now, by looking at the signal, I can clearly say that the noise is very prominent in which frequency band? 0 to 500 hertz band. Whereas it is significantly less in the second band, and it is very minimum in the third band. Now, for you, it is very easy. Looking at this, you can say that this is a noisy sign. The hearing aid has to do it automatically in real time. Okay. For that, what we will do is we are going to take the envelope of the signal. Okay. And then we are going to take the running maximum and the minimum. Now, if you see here, in the noisiest channel, the difference between running maximum and running minimum are the minimum. Right? Whereas in the clean channel, it is the maximum. Okay. Now, based on this, you give a gain which is inversely proportional to, or you give an attenuation which is inversely proportional to the difference between maximum and minimum. Provide an attenuation which is inversely proportional to difference between running maximum and minimum. That means wherever you have less difference, you give more attenuation. Where you have more difference, you give less attenuation. What does that mean? The noisiest channel will be attenuated more, whereas then you may be thinking, since you have found out the noisiest channel, why can't you remove that itself? But when you remove that, speech will also be lost, because some of the speech components, especially the vowels R, E, O, they all lie in that 0 to 500 hertz range. So if you remove that, you will not be able to hear the vowels properly, which will affect your intelligibility. So you are reducing the gain, you are giving an attenuation which is proportional to the noise rate. And after this, now it is in 3 different frequency bands. After this, you combine them. You are going to combine them. So when you combine them, what we are getting is this. Okay? Is it better than the previous one? The final output which you are getting is the bottom one after combination. So let us see whether it is better than the previous one. Okay, it is slightly better. This is all what you can do with signal processing. Here, the word was not clear at all. At least there you can see that some signal is there. So now the noise level has reduced to a level that you have sufficient difference between speech and noise so that you can hear. So this is all the hearing aid noise controlled signal processing does. The fourth task which you have to attend is about the feedback. When the microphone out, when the speaker also or the receiver output goes back to the hearing aid microphone, it generates a howling sound which is called the feedback. And this feedback begins when the sound goes back to the receiver. So to eliminate this feedback, what is being done in behind the ear hearing aids is that in the behind the ear hearing aid, the microphone is here, this is the microphone, and the earphone is here. So from the earphone output, the sound is taken through this tube and given to the ear with the help of a small device called earbud. So this ensures that there is no path where the output of the earphone can go back to the microphone. So you're totally cutting off the path. So that is called acoustic sealing. So that is one way of correcting this, and that is the traditional mechanism of correcting this. Increase the acoustic seal so that the output of the hearing aid never goes to the input. Another way of correcting that is with the help of signal processing. So this howling sound which comes from these people have done research on that, and they have found that the frequency of this howling sound lies in the range of 2000 to 5000 hertz. Okay, so you give more attenuation to that frequency range so that the amplification, the feedback doesn't happen. But the problem here is that when you are attenuating 2000 to 5000 hertz, along with the howling, you are attenuating several sound sources, especially the sounds sa, sha, and all lie in that frequency range. And now we have an advanced technique called adaptive feedback cancellation. Okay, so this becomes active only when the feedback is there. So there is something called as a feedback model. The concept is like that. It continuously estimates the signal that is being fed back. And the signal which is being fed back will be subtracted from the output of the microphone. So this is your microphone. This is the feedback. Output of the signal goes to the input through this red bar. And whatever goes as input to the red bar, we are estimating with the help of this feedback model. And the same thing is subtracted here, which is before it is given to signal processing. Okay? So this always avoids the feedback. It continuously estimates that. So this is how it works. It employs an adaptive filter to cancel out the feedback. The adaptive filter continuously estimates the signal that is being fed back and subtracting the estimated value of the feedback signal from the microphone keeps it free from feedback. So this is how the algorithm works. It continuously estimates placement and continuously updates. So in hearing aid also it is frame by frame processing. The signals are processed in frames of 20 millisecond to 50 millisecond duration. So one frame comes, we estimate the feedback, okay, do the subtraction, give it for processing, then the next frame comes, that it goes on. The fifth task, which is very important in hearing aid processing, is to take care of our own voice. So when I'm using a hearing aid, when I am speaking, I don't want that much high amount of gain which I require to hear from other people, because first of all, what I am speaking is known to me. Okay? So if I am hearing my own sound with later people, it becomes a noise sense for me. That effect is called occlusion effect. Many people will not be able to use the hearing aid because of this occlusion effect. So what you have to do is you have to identify your voice. Okay? So the microphone has to identify your voice. So here we use the speaker recognition technique. Okay? So the speaker is identified. So when I am speaking, it is the hearing aid identifies me as the speaker and then reviews the gain. So whenever the patient is speaking, through data sharing, processing and analysis, the hearing aids identify the signal and apply a dedicated setting which differs from other sounds. Okay, so for my sounds when I am speaking, the device has a separate setting. For other sounds, the device has a separate setting. How the device identifies my speech? Through speaker recognition. Okay, so that is what is done. And this technology is called own voice processing. So to process your own voice, you have a different algorithm and a different setting. Okay. So we have gone through the 5 major signal processing tasks in the hearing aid. We have seen how the channel separation is done to assign gains for different frequencies, different gains for different frequencies. We have seen how the dynamic range is compressed. We have seen the noise reduction techniques using the microphone and using the signal processing. We have done how the feedback is cancelled through adaptive feedback cancellation techniques. We have seen how own voice is processed separately compared to other sounds. Now we move on to the next topic, what is the role of artificial intelligence in signal processing? Can AI do something better in signal processing and hearing? So AI functions which can be implemented into the hearing. Some of the hearing aids, some of the functions are implemented, but not implemented in all hearing. So this is one research area or problem statements, set of problem statements which you can work on. The first thing which you can do is the real-time adaptation. Okay, so I have mentioned somewhere in my talk that when you are wearing the hearing aid, you are passing through different situations. Okay, and for each situation, the hearing aid has to be adaptive. It has to understand that situation and tune its processing, which fits into that particular situation. That is called real-time adaptation. So in real-time adaptation, it has to scan the environment continuously at the rate of 700 times a second. So in a second, 700 times you have to scan and then identify the environment and switch automatically to that environment. So that means when I am in the class here, change the settings to that. When I'm going to take the bus from the bus stand, it identifies the bus stand situation and changes that. That is one thing which AI can integrate. The second one is the speech enhancement. So now we have seen that we have to suppress the noise and take the speech from it. And in the reform which I had shown, it was very clear to you that the amount of suppression which can be done is very less. Okay? Now to make this more effective, you have to do enhancement of speech. And this can be done with the help of AI. Okay? So you can train your DNN, which was always on more number of samples and how the speech can be enhanced in all those samples that will help you to do the speech enhancement. The third one is the noise reduction. So AI algorithms can reduce various type of noise without compromising the target speech. Okay? So what the hearing aid was doing, identifying the noise in which frequency band the noise is being done, that can be done with the help of AI also. Signal processing is not required. Because if you have samples saying that, say in this sample, it is the noise is more prominent in this particular frequency band. So if you have more number of data, without doing signal processing, you can identify the noisiest channel. So this is again one area which you can work on. No one has worked in this area. Then the next one is personalization and self-learning. Now, as far as I am concerned, my routine is fixed, right? Morning I get up, get ready, come to office, work in the office, take classes, do research. After that, while going back, I do some shopping, take things for my home, then reach home, listen to TV, okay? Quarrel with whoever is available in the house, okay? And finally go to bed. So that is my routine. So AI can understand my routine and then program the hearing aid as per my routine. So that is called personalization. Okay? This again no one has done till now, so this is a research problem which you can work on. The next one is called environmental scene analysis. See now, the first issue I have mentioned that the AI should be able to identify the situation. So this is done with the help of scene analysis. You take a sample from there, you do the analysis and find out which situation it is. Okay, suppose I'm in a bus stand. You record a sound, the hearing aid will pick up a sound sample from there and then find out from the sound sample to which situation it belongs to. So that is done with the help of scene analysis where AI is very helpful. And the last one is integration. So now you have so many smart devices. You have Alexa at home, you have smart TV at home. Okay, so all this can be integrated with the hearing aid. So when you listen to the TV, when you listen to the hearing aid in open air, the listening will not be comfortable. If the output of the TV can be integrated with the hearing aid with the help of Bluetooth or some Wi-Fi mechanism, then the listening becomes better. So this is just one example of how real-time adaptation is done using AI. Okay, so how to identify different sounds. It is said that there are 12 million categories of sounds which we are exposed to in our day-to-day life every day. So if you have samples for all these 12 million categories, and if you are able to categorize them, for example, bus stand in a village, bus stand in a moderate city, bus stand in a busy city, bus stand in a tier 1, tier 2, tier 3 city, like that, if you classify different sounds, then the environment detection will be easy. So identify the characteristics that makes each of these sounds. Now we move on to the last topic, that is about the gaps in current hearing aid technology. So the major gap which is there in current hearing aid technology is concerned with listening in noise. So this study, which is published in 2025, so this is again this review study, which was published last month only. Okay, so you can refer to this also, how they have done the systematic review. So they say that despite all these technological advancements, individuals who use hearing aids have the difficulty understanding speech in the background. So that is the major challenge which still remains as a gap in hearing technology. It do not meet the expectation of the user. Okay, so you have seen in the video why this happens, why we are unable to, when we have hearing problem, why we are unable to listen to the desired speech noise, because the hair cells are giving instruction to the ear. The ear is unable to receive that instruction to suppress noise because the hair cells are missing. Okay, so in such situation, the hearing aid has to take up that job and do, and whatever has been done till now, it do not meet the expectation of the user. So since this is the main issue, future research should address the challenges of understanding speech in noisy environments to enhance the overall satisfaction. So you may be wondering, now we have very good devices available for listening to music and all. Okay, the music which we listen to from mobile, they are all very high quality music or high quality speech which we listen to. So this, I'm using this public address system you are listening to me. It's very high quality public address system, sound system. The hearing aid is also a sound system, but the limitations there or the constraints there is, one is the size, second is the processing time, because for this system the processing time doesn't matter. You can take even 100 milliseconds of processing time there, but in a hearing aid it has to be less than 8 milliseconds. So within all these constraints, with the help of AI and with the help of other signal processing technologies, if we can address this gap, it will be good for millions and millions of people. There are 400 million of people who will be using the hearing aid in 2030, and we will be one among them, because when we reach the age of 45 to 50, definitely we are going to have hearing problems because of the conditions, the environment conditions now, because we are exposed to a lot of high loud sounds in our day-to-day life compared to our parents. So these loud sounds, continuous exposure to loud sounds will definitely create problems in our hearing system, and we would be the probable hearing aid users after 5 years or 10 years or 15 years depending on your age. So whatever research contribution you do to this field is going to help you when you become a hearing aid user. So with this, let me end this talk, and thank you all for the patient listening. If you have any questions.
Is it possible to reduce the noise by identifying the objects inside the sound?
Yes, it's very good. So that is called scene analysis at present day. So if with A, if you can identify the objects and map the sounds produced by that objects, very good. Because if you identify bus, you know that it is either in a road or in a bus stand. Okay, so based on that, you can do that. That's very good.
If you work on this, which one popular data sets are available in public?
Data sets are very good.
Can you suggest any one?
I don't remember exactly, but there is a data set which gives you the sound scenes in most of the public places. But those data sets are not the data sets of our country. Let's say European data set. So the bus stand there, the difference you have to imagine. Bus stand in London and bus stand in Delhi, there is a lot of difference. So if you have to, if at all you are using that data, you have to do data adaptation. But data sets are available to start your work. I can send you the name of the data set. Okay, sorry.
Sir, I have a question. Sir, we know general purpose processors use ARM x86 or RISC-V ISS. Which ISS does this DS processors use?
Okay. So here again, there are two issues. One is the size issue, and second is the power consumption issue, because this works on a battery. So it's a small battery. Since the size of the aid is small, you have to use a small battery. And when you use the small batteries, the backup time is very less. Okay. So when we use those kind of processors, ARM processor and all, power consumption is much more. So these are dedicated DSPs which are built for this purpose. They are not general purpose DSPs. Okay. So you have to develop your algorithm in general purpose DSP, prove the concept, and then you can implement it. These are DSP specifically fabricated. These are R6 fabricated for this.
So it's custom yes.
Yeah, that's why it says custom. So each manufacturer will have. Okay, thank you so much. Thanks to Patil sir for giving us this opportunity to be with you.